How dangerous is Friday? Oh, whoops. How dangerous is Friday the 13th, really? Obviously, the fear of the number 13 goes back a long time, centuries, millennia ago even, and now it holds over into the Friday the 13th. And it's this kind of triskaidekaphobia, it's called, that has a lot of people wondering whether or not more bad things happen on Fridays the 13th. Well, millennia after this certain fear became kind of a cultural meme, now we can actually test it. So how would we operationalize something terrible happening on this very specific day? Well, we could look at things that are terrible that happen to us. Say more emergency room visits, more car accidents, and those kinds of things. Well, now we can report that as early as 2011 and 2012, there are two separate studies on this very topic. One looks at the number of emergency room surgeries over time based on Friday the 13th dates and compared as a control to other Fridays and other dates that aren't Friday the 13th. Obviously, what they found is that there is no difference in the number of emergency room visits and surgeries, emergency room surgeries, related to Friday the 13th. And similar data can be found for car accidents. Now, given the preponderance of data right now, as far as I know, there doesn't seem to be anything that really points to Friday the 13th being an actual dangerous date. And, you know, something based on superstition, it doesn't really surprise me very much. But what does surprise me, and might surprise you, is that there is an actual effect that Friday the 13th has. It's just a little bit more subtle. So there is a cultural idea that Friday the 13th is dangerous, that something bad could happen to you. So what actually happens on Fridays the 13th? Well, some estimates from institutes like phobia institutes, I didn't even know those existed, say that there is an estimated $700 to $900 million loss in the US, business loss based on productivity time, because people are not traveling, refusing to go on airplanes or drive long distances, being more careful. So this fear of Friday the 13th is actually having a risk aversion effect such that Friday the 13th might actually be safer than other days of the year because people are afraid something bad will happen to them, and so they do not engage in risky behavior. So is Friday the 13th dangerous? Well, if you run into this guy, then and you're a teenager at a camp, then yes, very much so. But for the rest of us in the real world, it might actually be the opposite. Friday the 13th might be one of the safer days. And you don't have to make 10 sequels to figure that out. Hello and welcome to the live show of Because Science. Ooh, we're doing all of your nerdiest comments, corrections, and questions off the top of my head right here on this YouTube channel. Look, I'm not an expert. I'm not a working scientist, but I know a little bit about a lot of sciencey and pop culture-y things, as we like to do on this channel. So if you have any questions for me on this Friday the 13th, please put it in the YouTube chat or wherever you may be watching, and Voice of the Void Nate will hopefully get to it if it's a great question and you're not spamming the chat. What up, Nate?
What's up, Kyle? How's it going?
Hey, what's our first question?
Wow, witty banter going on right here.
Hey, it's been a long day.
From Crazy Face McGee.
Already interested.
Why are there so many different ways to measure radiation? Why not standardize?
Now, this is a Crazy Face McGee if there ever was one. This guy right here, Mr. Voorhees.
And you would know.
And I would know. Don't tell me I don't know. I would know. There are a lot of different units for radiation, and some of them you may have heard of would be from the rad to the gray to the sievert. And while I'm not an expert on radiation, I do talk about radioactivity and nuclear weapons and all that stuff a lot. While I'm not an expert, what I can say is the difference in these units, why don't we have some kind of standardized be-all, end-all unit? Well, these units are based on how they affect material in a certain way. So you can use rads or grays or sieverts to measure, say, energy deposited in some amount of material in the human body, and one unit might be better. But if you want to measure an entire body dose, that might require a different unit. If you want to measure radioactivity just as particles per time flinging off of a thing, still another measurement might be needed. So there are specific units that we use when we're talking about the effect of radioactivity on humans, because you can calculate, say, the energy in joules deposited in a square centimeter, a cubic centimeter of tissue, for example, from something. But if you want to know how radioactive something is or its emission rate, then that requires different units. There just happens to be a lot of them because radiation does a lot of stuff to a lot of things bad. So you need a lot of units to capture the different ways that it can interact with different materials. Although I will say that many of the units you might see out in just articles and magazines and popular culture in general, like the rad, aren't used as much anymore. So these units do evolve over time and move towards standardization, even if it's not minimization of the number of those units.
This next question is going to be a little long one.
Great.
From Tom Poe.
Okay.
Love the show.
Thank you.
If you built a massive ring around the Earth,
okay,
exactly equal distance from the ground on all sides,
okay,
would it float because gravity is acting equally on it from all sides?
What? Oh, no. No. So if you had, well, I don't mean to dismiss you. I think you're on the right track. But if you have something like the planet Earth, and you want to put a giant ring around it because you're not a supervillain, you're not. You just want to build a megastructure. You put something out here, a ring around the Earth, equal in distance in all sides. Now, if you accomplish that, ask yourself, what is keeping gravity from pulling this ring down to the center of gravity of this system, which is the Earth? Nothing. What's the opposing force? Nothing. But what you could do, and what there is an actual limit, and this defines a kind of orbit around the planet, what you could do is, instead of just putting a ring around Earth, you could put a bridge around Earth in a ring. And I say bridge because this bridge would be attached to the Earth itself. Now, if you do this, this ring will be spinning because it is attached to the Earth, and the Earth spins very quickly. At the equator, it's about 1,000 miles per hour. That's very fast. You know, if you've ever been on one of those weird carnival rides that you may not have thrown up on, you know who you are, that if you are inside of a spinning ring, you feel like you are compelled to be flung towards the outside. This is, depending on your reference frame, your inertial reference frame, this is a centripetal or centrifugal or whatever you want to call it, a centripetal force, centrifugal force, I think is the corrector. Now, once you have this, because this is attached and it's spinning, this matter, this bridge, this ring that we're creating, also feels like it wants to be flung outwards. And so you could come to a point where this centrifugal force is balanced exactly by the gravitational force. And this is an orbit that we use for satellites and stuff. If we're putting something around Earth in such a way, well, no, I may be misspeaking. Rather, this is the distance where we have hypothesized that we could put a space elevator. So I misspoke about satellites. A space elevator would be tethered to the Earth and spinning, and at the point at which the gravitational pull on all that material is equated by the centrifugal force, you would be weightless inside of that part of the space elevator if you were going up of it. Away from it. And if you moved past that point, you'd be pulled in one direction. If you moved downwards back towards Earth, you'd be being pulled back towards Earth more than you were being pulled upwards. So yes, if you built a ring, there would be a point around Earth at which you would be weightless if you were in that ring. However, the ring needs to be spinning and attached to Earth to get that centrifugal force to equal and opposite the force of gravity on all of that material. And this would require, mind you, crazy engineering. If you think about it, all this stuff is going to weigh a lot. So it's going to be a lot of just moving material around. And the Earth is spinning very, very quickly. So the centrifugal force, the tension, if you need this to be very high in the air, the tension could be extreme. So right now for space elevators, we don't even know of any known material. Carbon nanotubes start to get close, but we don't know of any material that could handle all of the necessary forces and not be ripped apart and flung into space. So this would require advanced engineering that we do not have right now, but in theory you could do this kind of thing and you're right on track, whatever your name was. I forgot, I've been rambling. Whew. That was a long one,
That
you
was
were
a
right.
good one, yeah.
Yeah.
From Christopher B.
Hello, Chris B.
Can you use asteroids to heat up and add mass to Mars?
There's a lot of space questions.
Yeah.
Am I a spacey boy now? Hey, why not? Chris B, one of the options or one of the ideas for terraforming Mars is exactly what you say. And we do mention this in our Nuking Mars episode, that you could redirect a number of asteroids, say maybe made out of ammonia ice, to Mars to add energy in the form of their impact when they explode to the surface and heat up the surface, but also add the kinds of chemicals that you would need to start terraforming. And why they suggest ammonia is because ammonia, when it evaporates, it's a powerful greenhouse gas and might kickstart the feedback loop that you need to start heating up the planet more and more, such that we could go to the planet and not immediately freeze to death and then have all of our moisture boil off of our eyes and our tongues like that. You wouldn't want that to happen. So yes, asteroids, moving them towards Mars is one of the ideas that has been considered. However, just like building a gigantic ring around Earth would be hard, finding asteroids, the correct asteroids, going to them, tethering them or gravity tugging them all the way back to Mars in the right way in a short-ish amount of time, if you want to, see the end of your project and it doesn't take 1,000 years, would be incredibly complex and difficult. So all these terraforming ideas are incredibly difficult. In fact, the most recent papers say we cannot even come close to doing it with today's technology, and we probably won't even do it within our lifetimes. Probably definitely not. So I wouldn't bet, Chris B, on you and me seeing people on Mars. But hey, people living on Mars. We might live to see people stepping foot on Mars, and wow. Wouldn't that be a thing? There's probably first or second graders right now who would be like future Martians, like stepping on Mars. Isn't that amazing to think about? I think so, and I would know.
From Cage Caton.
Ooh.
Always been
Are
curious.
you a Mortal Kombat character?
Yeah, right?
Yeah.
What is your favorite branch of mathematics?
Gonna be honest here. Not the strongest math person. I know we do a lot of math on Because Science, but if you pay pretty close attention, you know that we never get really too complicated. I don't think we may have done calculus once. And that's because I'm not an expert, and I don't like going out of my field just to advance a point, because if I don't understand it, then I'm not going to be able to get you to understand it. At least that's my thinking. I prefer to understand things before I tell you them, otherwise I'm just a talking head, and the hair can only go so far, you know what I mean? So my favorite branch of mathematics is hard to say. When I was doing my education, I did do, like math 1, 2, 3, 4, calculus 1, 2, differential equations, that kind of thing. I did like differential equations quite a bit, but I guess I will say, this doesn't really answer your question, but some of my favorite classes where mathematics was heavily applied was probably thermodynamics. Thermodynamics is incredibly interesting to me, and it has so much power to figure out things that we care about. So I'd say thermo, and then heat transfer, which is hard. I don't like statics I like statics. I don't like dynamics. Dynamics is maybe it was the teacher. I don't know. What's his name? Who cares?
From Alexandros O.
I remember his name. I'm just kidding.
If you could ignore one human need, hunger, sleep, etc.,
Yeah.
which one would you choose?
I thought it was going to be, if you could ignore one human being, who would it be?
It's me.
It's you. I mean, I didn't want to say anything. If I could ignore one human need, what would it be? I don't like eating. Eating is boring to me. And a lot of people get on my case for that. It's like, why do you just like very plain foods, and why aren't you like a foodie and enjoy the spectacle and the taste and everything, like Food Network style? It's like, I'm a coal furnace into which calories must be shoved, and then I'm good to go. I could forego eating. I wouldn't miss it, I don't think. Just keep on chugging along. Just like the conductor no longer has to shovel the coal into my metabolism. What is food if not a conductor of your metabolism, shoveling coal into your brain? I don't think that works.
From Robert D. Wilson.
Thanks for saving me on that one. Frequent commenter, Robert T. Wilson, I believe.
They love the hair.
Thanks.
Could a human take all of their hair and lay it end to end and reach the moon?
Oh, you nerd snipe me. All right, so this is a classic nerd sniping. I don't know how many follicles are on the human head. But so this is a wonderful time to do one of my favorite activities, which is called Fermi estimation. It's named after Enrico Fermi, a very, very famous scientist, incredibly smart, a genius, level intellect kind of person. And he came up with a way, he often had this little trick that he would do, and it came to be known after him, called Fermi estimation, which is making decent assumptions, even if you don't know the exact answers, using basic mathematics, and then coming within a few percentage points of the actual answer without knowing any of the real data. So why don't we try that for this question? And so we have to come within the ballpark. We have to make a good estimation of all of our variables. So we know, I would say that we know, let's just do the hair on my head. So I would guess that there are more than 1,000 follicles of skin follicles on my head. But there is probably less than, let's say, 1 million. And so I know this is a huge range, but we're just trying to get within something that we can live with. So between 1,000 and 1 million. All right, so let's go somewhere in between that just to start. Let's say it's 100,000 hair follicles, which could be within a few percentage points of, 20, 30% of what it actually is. It doesn't matter if we're being diligent with our assumptions. Now, 100,000 hair follicles. How long is my hair? Well, based on how I'm looking at it right now, hey, let's do some fun estimation. Well, I know that my forearm right here, which way to the beach, am I right? I know my forearm is almost exactly 1 foot long, and if I put my forearm near my hair, it looks like my hair is maybe around 1 foot long, maybe a little bit longer than that. So a foot is, this is fun. I like doing Fermi estimations with all of you. This is better than what? Anyway, so a foot is 1/3 of a meter. So now we want to multiply this by 100,000. And if we multiply this by 100,000, we move it over 5 decimal places. So we're going to go 1, 2, 3, 4, 5. 30,000 meters. Now this is a lot. This is 30 kilometers. But the moon, I think, is 384,000 kilometers away. You'll have to check me in the comments. But it is definitely an order of magnitude further away than this distance. It's between 200 and 300. Oh, no, sorry. It's even worse than that. So this is only, I misspoke, and that's why we're doing this together like this. This is only 30 kilometers, right? 1,000 meters here. So this is only 30 kilometers. So if the moon, and Nate, if you want to look this up at any point.
It's
384,000 kilometers away?
384,400 kilometers away.
Bam! 384,000 kilometers away, just like I said. So this is 30. So we are way away. We are tens of thousands of times smaller. If you laid all of my hair on my head end to end, it wouldn't come within 1% of the distance to the moon. So, since all of the hair on the rest of my body is longer than this, I mean, I can't prove that to you, but you're going to have to assume that the hair on my head is the longest hair on my body. Even though there might be more follicles, they are necessarily going to be a lot shorter than this, which tells me, if we're still doing Fermi estimation, that this number is not going to be that much larger. Even if even if it goes up to 100 kilometers, we are still so far away from the moon because it's, like I said and nailed, 384,000 kilometers away. So, if you laid all the hair on your body end to end, you would not even come close to reaching the moon. And we did that without knowing, and we did that without really knowing how many follicles are on our heads or anything like that. This is, if we actually looked up, which someone could do, how many follicles are on the average human scalp, we would know that we're probably within a decent percent of the actual value. And while that happens, we can go to the next question.
From Star.
Woo.
Since we're on a subject of unluckyism, what is your favorite superstition?
That's not a word. Well, I don't like superstition to begin with. I think superstition in our society leads to grand systems of thinking uncritically and advancing solutions that don't actually advance human health or well-being or anything like that. I don't like superstition at all. I'm no fun at Halloween. No, but like I think superstitions can be harmless, but they can also be harmful. That being said, my favorite superstition, I don't know. I mean, I'm not a superstitious person, but there are definitely odd ones, and maybe one of the oddest ones I've ever heard of is, I believe in South Korea they firmly believe, or at least some percentage, small percentage of the population firmly believe, this could be overblown in the media, but some percentage of the population firmly believe that if you leave a fan on at night and you go to bed, it can kill you. How? I don't know. But I think there have even been warnings put on some fans. I might be misspeaking here, but there may have been actual warnings like, turn off your fan before you go to bed or else you can die. That is a weird superstition. So that's up there for me when you point out, I don't know if that's an optimal way for a person to behave. Who knows? How many follicles are on the head, Nate?
100,000 hairs.
What?
Yeah.
Wait. Can you repeat how many follicles are on the average human head there?
100,000.
Oh, that's what I'm talking about. Fermi estimation, baby. We can get close to, so this is the actual value, basically. So we did it. We did it. I feel good about that.
I'm so proud.
Yeah. This is right though, right?
From Aaron Reel, what's the science behind a second wind?
Oh, yeah, no, that's weird. Second wind, so if you're not familiar with the concept, I don't know, you might not be. When you're super tired and then for whatever reason, or you're exhausted for whatever reason, you spring back into action and you're able to jump back into the game or, go out to the next bar or, you come alive in some other way. I have no idea. I would guess, like everything, it is a combination between the psychological and the physical, where for some reason you could get suddenly excited by something, release, adrenaline into your system and become more alert and alive and awake and enthusiastic. If you ever did that practice at day camp, maybe it was just me, alive, awake, alert, enthusiastic. Remember that? So I think a second wind is probably just a combination of psychological factors and physical ones, such that when you think you are really, really tired and you can't do anything, there's probably still some reserve left in you that if triggered, you can still go on and do something. And I think maybe psychologically we believe that when we're tired, that's it, but we don't really know the reserves that we have. There might be some mismatch between what we expect of ourselves and what we can actually do, because in our day-to-day lives, we don't push ourselves to failure. We don't push ourselves as hard as we can go. And so when you can run that extra half a mile or whatever, you're like, wow, I didn't know I had it in me. Well, you literally didn't know you had it in you, and now you do. So I think second wind is something like that.
From Kano.
From Mortal Kombat?
Yeah.
Oh, wow. How's that eye laser? I want one.
How hard or fast would you have to punch to pop a balloon?
Weird. Weird. Okay. So there is no way I'm going to be able to do this in real time for you. This sounds complicated. But so the problem with a balloon is it sounds like a Twitter thread that I would never read. The problem with balloons, story time. So when I was a kid, so the problem with balloons is that when you impact a balloon, the rubber is obviously very elastic, and that will absorb some of your kinetic energy and then return to its state once the force is removed. But because it is not tethered to anything, it's not against a wall or what have you, when it pushes back on your hand to return to its state, because the state of elasticity. So let's get technical here. So if you drew a graph of a material, of the force on that material versus how much its length changed, which is called the stress over strain, you will usually, for most materials, see a graph that looks something like this. And what this graph means is that in this region here that looks almost linear, just like at a 45-degree angle, as you put force on it, it changes at a regular rate. It stretches at a regular rate. And for most materials in this range, that when the force is taken away, the length returns very quickly. So rubber is elastic in this way. You can put force on it and it will change its shape, and then when you remove the force, it just goes whoop, back down, and then the shape returns. But for something like metal, you can do that, but then at a certain point, there's so much force on it that the length starts to change a lot and then doesn't go back. This is when metal fails. When you can try to bend a piece of metal, let go, and the metal retains its shape. But if you bend it hard enough and then it goes, it deforms and stays deformed. That's this part of the graph. All of that being said, so when you touch a balloon, it stays in this elastic region here, and then when it rebounds in that elastic region, because nothing is behind it, it pushes off of your hand, and then in that moment, you are necessarily lowering the force on the surface of the balloon, and that force over a certain area is pressure. So what you would want to do to pop a balloon with a punch is hit it so hard and so quickly that as the balloon moved away to undo this elastic deformation, that the pressure is still such that it can puncture rubber. And I do not know what that speed would be. I would guess your best shot would be, since you can't punch super fast, you would want to try to instead change a different variable, which would be area. So instead of punching like this, maybe you want to punch like this and try to punch poke a balloon, because the same force over a much smaller area would increase the pressure dramatically. And I wonder if that's something like Shaolin monks can do or something like that. They don't. Nope, I'm not gonna go on that. Punch poke a balloon, maybe you'd be able to pop it. I bet the speed is undoable for people though.
Last question.
Okay, well, wait. Shaolin monks, when they throw the needle through the glass, I saw the slow-mo of that on the internet. I think the slow-mo guys did it. And if you've never seen it, they're supposed to be able to throw a needle through a pane of glass, and on the other side a balloon pops. But when they showed it in slow motion, they're like, hey, they did it. But if you look at the slow motion, the needle hits the glass, doesn't go through, and then parts of the glass pop the balloon. So they're not doing it. Just want to make that very clear. It seems too hard to do, because it is. Last question. Sorry.
Last one. From Robert Belfin Jr.
I got a lot of problems.
Love the show.
Thank you.
If you were a supervillain, if and only if.
Of course, if. This is totally hypothetical.
Who would you choose to be your number 2?
That's a good question. I mean, obviously, Elon Musk is up there as an immediate option for who your number 2 supervillain right-hand person would be. I know. He is a philosopher called Nick Bostrom, and I suggest you look him up. He's incredibly intelligent, and he is the guy who came up with the simulation hypothesis. He is the one who popularized the idea, Musk took it from him, popularized the idea that we might possibly be living in a simulation. If you look him up, if you look up his other papers, he has other incredibly mind-bending ideas that are definitely super villainy. Like, what he can calculate the actual chances that the next technology that humans discover might wipe out all civilization. That's the kind of research he does. So I would pick Nick Bostrom. If you don't know who he is, look him up. Look him up on YouTube. Watch some videos. Very, very smart man. Came up with the simulation hypothesis. But this is all theoretical. I'm not a supervillain, okay? Just because the next 2 episodes coming up on this channel may be pretty rough in the supervillain camp, doesn't mean I'm a supervillain. So thank you so much for watching this episode of Because Science Live. This is one of my favorites that we've done because we got a lot of great questions and we came up with a straight up accurate Fermi estimation for your hair in the moon. I'm very proud of that we were able to do that together in real time. Let's do more of those estimations in the future and hopefully I can do multiplication correctly. Have a wonderful rest of your weekend. Next week, we got more of the same. We have a new vlog, new footnotes, a new main episode, and a new live stream. I will see you then, but until then, have a wonderful rest of your weekend, as I said, and be nice to each other because this is all we got. And be careful. Be careful today. Even though something probably won't happen to you. Just be careful.